All right, last question for the day. We've got a burglar that's trying to haul a safe up a frictionless ramp to their getaway truck. Okay, so here we go. We've got our mass. The ramp is tilted at an angle of theta. Ooh, that's interesting. And we are going to answer the following questions in terms of theta and universal constants. So this is one of those ones that you guys love. No numbers. We're going to go straight into trying to answer each of these questions. Okay, so they are trying to haul it up using, it says, the tension in the rope. So we have to assume that they're trying to use some kind of rope to pull it up. So I'm going to add that in there, that we've got some type of rope pulling up. What is the tension in the rope if the safe is at rest? Okay, well, in order to do that, I think we're going to need to do a free body diagram. So we've got the normal force pointing up this way. We've got gravity pointing down. And then we've got tension, which is pointing up and to the right. Remember, we're going to tilt our axis like this. So we've got horizontal and vertical. Notice that the only force now is the force of gravity that's off kilter. The normal force is purely vertical and the tension is purely horizontal. This is why we tilt our axis. All right. Now, in order to find out the tension in the rope, if it's at rest means acceleration equals 0. Now, tension in the rope is horizontal, so I'm going to look at the horizontal forces here. So I'm going to go sum of the horizontal forces is equal to the mass times the horizontal acceleration. If it's at rest, that horizontal acceleration is 0. The mass is capital M, so I'm going to put that in for the mass here. And then the forces, the horizontal forces, I've got tension pulling upwards, and then I've got here the horizontal part of gravity pulling downwards. Now, you can define up and down to be whichever direction you want. I think the purpose of this is eventually we do want it going up the ramp. So I'm going to define up the ramp as positive and down the ramp as negative. And I know that's different than what we did in the last ramp that we did, but recognize that you can define it however you want as long as you're consistent throughout this problem. Again, I like to make acceleration be positive in the direction that I expect it to go, and that's completely fine. So tension is going to be positive. The force of gravity in the x direction is negative. Now, the 0 times the mass is going to go away. So what I'm going to end up with is tension minus the force of gravity in the x direction. Notice that that is the opposite side of my angle theta here. So I'm going to be using sine. So it'll be Fg sine theta, and that needs to be equal to 0. I can move that over. I now have tension equals Fg sine theta. Fg I need to rewrite. That is not one of the things that they gave me in the problem. So I'm going to write my final answer is that the tension is equal to the force of gravity, which is mass times the acceleration of gravity times sine theta. And so there we go. That's the answer to letter A right there, is that if it is at rest with no friction, remember we've got no friction here. If we've got no friction, then the tension needs to be equal to mg sine theta. Otherwise, the block will slide down the ramp. If you have more than that, it'll accelerate up the ramp. Now, question B says, what is the tension in the rope if the safe is moving with a constant speed of 1 meter a second? Don't you dare start doing more calculations, eh? It says constant speed. If that's constant speed, what is the acceleration? The acceleration is 0. Therefore, the calculation will look exactly like what we have here, and we'll get exactly the same value. Remember that if forces are balanced, either it's at rest, staying at rest, or it is in motion, continuing to move with that motion. And I know it feels a little counterintuitive and it feels like that is weird, but as long as those forces are balanced, it's going to continue doing what it's doing. And don't say, yeah, but gravity's pulling down. No, tension's pulling up. Tension is balancing whatever gravity is doing. And so you cannot say it's going to slow down because gravity's slowing it down, because there is something else balancing whatever gravity is doing. Okay? Now, the next question does ask us to go a little further. It says, well, what is the tension in the rope if it is accelerating up the ramp? So we're going to change it just a little bit, right? We're still going to do the same. We're still looking at tension and gravity here, but we're going to say sum of the forces in the x direction is equal to the mass, which is m, times the acceleration, which is 1, right? In this case, we do want acceleration. I've made it positive because remember before I identified going up the ramp as positive. The sum of the forces still is tension minus Fg in the x direction, which will be equal to just the mass times 1, which in this case is just the value will just be the mass. I'm going to add that Fgx over to the other side, and so the tension will be equal to m plus, and then remember Fgx was that Fg sine theta. Now notice that when I rewrite it here, it's just Fg. It's no longer Fgx because I've written it in terms of the original gravity, which then this Fg can be, of course, replaced by the mass times the gravity. The sine of theta is what's going to adjust it so that we just get the horizontal piece of that weight, which is mg. All right, you could rearrange this if you wanted. Sometimes AP will ask you to show that it looks like this, m times 1 plus g sine theta, right? Something like that you could do. All right, now this is an interesting question because this could be one of those experimental design questions. They could ask you to measure different angles, for example, and different tensions. And in that case, the tension would be your y, the angle could be your x, or maybe the sine of angle is your x, and then the mg would be your slope, and the m by itself would be your y-intercept, right? This is kind of that idea of linearization. Remember that that can come in with any equation or any set of things that we can set up given the knowledge that we have. So yes, this is not part of this question, but I think it's important to recognize that that idea of linearization can pop in anywhere. If I graph y versus sine of theta, and I just do sine of all my angles, that will give me a linearized graph where the slope is mg and the y-intercept is the mass. Kind of a cool thing there, right? Assuming that the acceleration is always at 1 meter a second, that would change the tension required at specific angles. All right? Now, let's go on and look at D, because that's really what we're aiming for today, is getting that friction stuff in there. So what if instead there's a static coefficient of friction of 0.8 and a kinetic coefficient of friction of 0.5 between the safe and the ramp? What force is necessary to get the safe moving? Now, again, recognize we're going to add in friction. If I'm trying to pull it up, that means that we've got some friction that's going to resist. That's going to be in the leftward direction. So it's going to be a very similar equation to what we've been doing, some of the forces in the x direction. But now I'm going to have tension pulling up. I have that force of gravity in the x direction pulling down. And I have friction going in the down direction, which is equal to max. Now, any amount of acceleration is going to be enough to get it to start moving, right? And so I'm going to go ahead and set this equal to 0 because I'm going to find out exactly how much will give me 0 acceleration. Any tension that's more than that will automatically cause acceleration. Okay, now in order to do this, we're going to have to fill in some numbers, right? We've got the tension. We know that that Fgx is Fg sine of theta because we've been doing that. But this F is not allowed. That is not a universal constant. It's not given in the variables that I started with. So what I need to do now is I need to figure out, well, how much friction is there? Well, please remember that friction can be equal all the way up to the coefficient times the normal force. Again, we want to get it to start moving, which means that it's static friction until the point when it's moving. So again, we're looking at static friction. So we're going to use the coefficient of static friction because we're not looking at when it's moving. We're looking at when it's rest until that moment in time when it starts moving. All right. So the force of static friction is going to be equal to that coefficient of static friction, which is 0.8, times the normal force. Now, don't go putting the weight in for the normal force because the normal force is not equal to the weight, right? The normal force is vertical here, which is equal to the vertical component of gravity. Now, you can work that out. Hopefully, you're getting a little bit more comfortable and you're comfortable enough that you can now say that's just Fg sine theta. Sorry, not sine of theta. I've used sine of theta too many times. Cosine of theta. All right. Now, that's because it's the adjacent side. That will allow us to get that adjacent piece, which those are the only two vertical forces, the normal force of the ramp and that vertical component of gravity there. So this, we're going to take one more step. We're going to say the static friction is equal to 0.8 times, again, mg, because it needs to be in terms of the variables that they gave us, cosine theta. We can now put that in for our force of friction. So we're going to plop it in over here. So we're going to go 0.8 times mg cosine of theta. That needs to be equal to 0. And now I can solve for the tension. The tension needs to equal that Fg. I'm going to move that to the right side, and I'm going to move this to the right side. So it's going to be mg sine theta plus 0.8 mg cosine theta. So if I had the mass and if I had the angle, I could now calculate the tension required. Any value more than this will allow the safe to start moving. And so you want to recognize that that's what we're looking for. Now, you have to get used to this idea of not having values. You have to get used to the idea of being able to work through this with variables. Okay? Now, letter E asks us one final answer. If they continue with the force calculated in D, what will be the motion of the safe once it starts sliding? Okay, now we're going to talk about it first and then see what we can put with it. What will be the motion of the safe? Well, once we apply this force here, once we apply that force and it starts moving, it's not going to be static friction anymore, right? It now needs to be kinetic friction. Once it's moving, it's now sliding. So what does that mean? That means that because I have a lower coefficient of kinetic friction, it now means that my friction is less than it used to be. Okay, now this is the numbers that it's talking about. Because my coefficient of friction is 0.5 now instead of 0.8, friction is less than it used to be. If I maintain that tension that I calculated here, that now means that tension is going to be greater than the sum of the friction and the horizontal gravitational forces, right? Because this is now less. And so if this stays the same and these values decrease, I now have an unbalanced force and it will accelerate up the ramp. This should be consistent with what you've noticed in life. If you've never noticed this, I want you to go try to push your couch or your dresser or something large. If you've got a big box filled with stuff, you could do that. Try pushing it. Recognize as you start pushing it, it doesn't want to move, but as soon as you get it moving, it then actually accelerates. You stumble because of the acceleration of the box. If you keep pushing with the same force that you had before, if you keep pushing with that force, it will continue to accelerate. The thing is, we usually adjust and we then push it with less force. It's easier to keep pushing with that kinetic friction than it is to get it started. All right? And so that's all it wants you to do in E, is recognize that if we continue with that tension, because friction is less when it's sliding, the safe will accelerate up the ramp. Okay? And that's it. That's it for this question. I hope that these videos have been helpful for you. Let me know if you have any other questions. I'm happy to try to fill in the gaps or help explain anything if I wasn't clear enough. All right? See y'all next time.